Next, we're going to look at alternating series and how do we determine whether or not an alternating series converges. Now, when I say alternating series, it's a series that looks something like this. And we got n equals 1 to infinity, negative 1 to the n minus 1, 1 over n. And we say it's alternating because it goes back and forth between positive and negative. The terms, they alternate back and forth between positive and negative. So, for example, if you look at when n equals 1, we've got 1 minus 1, 1 over 1, and negative 1 to the 0 power is just 1. So this first term is 1. Of course, this here is 1. Now the next term, we've got negative 1 to the 2 minus 1, 1 over 2. And notice this would be negative 1 to the first power, and that would give us a negative. So this is a negative 1/2. And it alternates like that. You could generate the first few terms out here. And it just goes back and forth between positive, negative, positive, negative. Now, notice that this particular series here that I've chosen, this alternating series, it's alternating, but also notice another quality. Every term is less than the previous. For example, we've got these terms here. We've got 1, 1/2, 1/3, 1/4, 1/5, and I'm not paying any attention to the positive or negative. I'm just saying the a sub n, this part right here. Notice that every term is less than the previous. 1/2 is less than 1. 1/3 is less than 1/2. 1/4 is less than 1/3. 1/5 is less than 1/4. So every term, it is less than the previous. And that continues on. So notice that to be more general, we could say, well, let's just be more general here and say, let's suppose we've got this series, and instead of 1 over n, I've got a sub n. And notice that a1 is greater than or equal to a2, greater than or equal to a3, greater than or equal to, and so forth. So let's suppose that we do indeed have a series that has that property. In other words, it's non-increasing, right? Okay, it's monotonic. And furthermore, let's suppose that the nth term test is satisfied. Okay, so let's suppose this is true. So we've got these two conditions and we've got this alternating series. When those two conditions are met, this series will converge. When those two conditions are met, the series will definitely converge. Now, what we want to do is see, well, how do we know that? How can we illustrate that? Well, let's think about this series. We've got n equals 1 to infinity, negative 1 to the n minus 1, a to the n, a sub n. Now, let's just think about the partial sums here. The let's think about the first partial sum here. Okay, first partial sum is just going to be a1. The second partial sum would be a1 minus a2. See, it alternates. And the third partial sum, and we could just keep going, a1 minus a2 plus a3, and so forth. We could keep going on and on. In fact, let's just jump ahead and do s sub 8. Well, that would be a1 minus a2 plus a3 minus a4 plus a5 minus a6 plus a7 minus a8. Okay, that right there is the eighth partial sum. Now, let's just think a minute about the partial sums. And in fact, I would just want to look at the even partial sums. For example, this right here would be S2. If we add these two over here, that would be S4. And you can see how this goes. Then we add some more to get S6, a couple more, to get S8. Now you can see that if you look at this, if you think about the sequence of partial sums, you can ask yourself, well, what's happening to them? What's the difference between S2, S4, S6, and S8? Okay, so we've got the sequence of partial sums. Let's just look at it. This we've got S2, S4, S6, and S8. And what you'll notice about these is each partial sum, each even partial sum is getting bigger than the previous. So S2 is less than or equal to S4, less than or equal to S6, less than or equal to S8. Yeah. So what we have here is a monotonic sequence. Monotonic. It's a non-decreasing monotonic sequence. That's what this is. That's what the series of partial sums is. Now, let's do another rearrangement. Recall that we have S8 is equal to A1 minus A2 plus A3 minus A4 plus A5 minus A6 plus A7 minus A8. Okay, there's the eighth partial sum. Now, I want to do another rearrangement. So here's what we have. We have S8 is equal to A1 minus A2 minus A3 minus A4 minus A5. See, what I'm doing is I just put these two together and I put the negative on the outside. So you can see how they're the same if you work through it. Minus A6 minus A7, and then finally A8. Now, look at this. This sum right here, this partial sum, notice you keep subtracting off positive numbers. You start with A1 right here, and then you subtract off A2 minus A3. Remember, that's positive because A2 is bigger than A3. A4 is bigger than A5, so this one's positive, and so forth. And of course, A8 is positive. So you start with A1 and you start subtracting off positive numbers. So you know for certain that S8 cannot be any bigger than A1. Yeah, that's true. Now, that being the case, let me generalize this a little bit because what I'm doing here is I'm just talking about the eighth partial sum. But what if I wanted to talk about even partial sums in general? In other words, what does a general even partial sum look like? In other words, like you've got the sixth partial sum, the eighth partial sum, the 2nth partial sum, let's say. So let's look at that. We've got S sub 2n. This is just a formula for an even partial sum. And I'm going to kind of pattern it after this S8 so you can see. We've got A1 minus A2 minus A3 minus A4 minus A5. And we keep going all the way out to A2n minus 2, A2n minus 1, minus A2n. There. So that's me generalizing this eighth partial sum to be an even partial sum. Now, remember, what we have here is this thing right here. Notice we keep on subtracting positive things off. Okay, all these are positive. So what we know here is that S sub 2n is bounded. It's bounded. So we've got so think about these sequences, this sequence values. We have the even sequences. We have S2, S4, S6, S8, all the way out to S2n. And this sequence is monotonic. Every S keeps getting bigger. S4 is bigger than S2, S6 bigger than S4. This is monotonic and it's bounded, right? So this sequence is monotonic and bounded. That means that the limit exists. So let's suppose that this limit is equal to S. We know the limit exists for that sequence. This limit, we know it exists because it's monotonic and bounded. So there is that that's what we wanted to do. So look, in other words, I found a limit to the 2nth partial sum. Now you might say, well, you haven't shown the limit for the nth partial sum, and that's what we need to show the thing converges. Okay, so let's do this. We've looked at the even partial sums. Now let's look at the odd partial sums. And in particular, we want to look at, instead of the 2n nth partial sum, we want to look at the 2n plus 1 partial sum. Well, that's going to be the 2nth partial sum plus the 2nth plus 1, or the next term in the series. And that would be a 2n plus 1. Okay? So we just add the very next term in that sequence. Now, what do we have at this point? Let's go ahead and try to take the limit. Let's take the limit as n goes to infinity of s sub 2n plus 1. Well, that's the same as the limit as n goes to infinity of s 2n plus the limit as n goes to infinity of a 2n plus 1. Now, we've already found that this limit right here is s. And we also know that this limit is 0. Yeah. So here's what we have. We know that the sum, we have this. We have the limit as n goes to infinity of s to n equals the limit as n goes to infinity of s to n plus 1. They both equal s. So we can say, well, the limit then as n goes to infinity of Sn is s. In other words, we've what we've shown is that, well, we've shown that if the conditions for the alternating series are met, they're decreasing. We have an alternating series. Each term is decreasing, getting smaller and smaller. And if the nth term test is satisfied, condition is satisfied, then we have we can say the series converges.